weaker hyperbolas and interpret them as being from an object that has a similar K value as the soil, maybe rocks, clumps of dirt, something along those lines. But if I was looking for a utility that might be subtle, a fiber optic line, a non-metallic water line in a wet soil, or a non-metallic gas line in a dry soil, I should take a second look at these hyperbolas and collect more data to see if I see them again on parallel lines. If so, this would mean that they form linear objects, which usually indicates a utility. Okay, new topic. I know that you all know this because it's intuitive. GPR signals get weaker as they travel deeper into the subsurface. But let's just make sure we understand what's really happening. Reflections get weaker with depth. There are actually several reasons for this, but the dominant reason, and the one I want to talk about today, is called signal attenuation. The depth that GPR signals travel into the subsurface before they are completely attenuated or absorbed is controlled by the electrical conductivity of the soil. We know this more commonly as clay is bad for GPR, but the underlying cause for people to make that statement is that clay-rich soils generally have a high electrical conductivity. So here's an animation that shows what happens to the GPR signal as it travels in materials with different electrical conductivities. On the left, low electrical conductivity results in slower attenuation of the GPR signal and a lot of reflected energy making it back to the surface. We know that we can only detect an object in the subsurface with GPR if the energy reflects and makes it back to the GPR receiver on the surface before it gets completely attenuated. In the middle is a material with higher electrical conductivity. The GPR signal is attenuating, but a little bit of the signal makes it back to the surface. We would see this object, but it would be weak. You can just see a little bit of energy making it back to the surface. On the right is unfortunately what many soils are like. They have high electrical conductivity and absorb the GPR signal quickly. In this case, the GPR energy makes it down to the object and reflects, but it's completely absorbed before it makes it back to the surface. This object is invisible to GPR. Most GPR practitioners have been in this situation, trying to explain to the client why the GPR did not find the object they're looking for. The culprit is often soils with high electrical conductivity. The soil may naturally have high electrical conductivity, such as clay soils, but materials with high electrical conductivity can also be introduced to the soil. This sometimes happens when they add fill to an area to even out a surface. The native soil in the area may be great for GPR because it has low attenuation and allows the GPR signal to travel deep. But when you walk across a filled area and the penetration, decreases because it has higher attenuation. I've also seen the opposite situation, bad native soil, and the fill that was added is actually better for GPR penetration. This goes along with one of my messages today, which is GPR can be hard, but don't give up too quickly. Okay, so now that I've got the GPR reflectivity and attenuation out of the way, let's talk about a few concrete ways that you can get more out of your GPR utility data. Look at the bottom of this GPR line. What is the signal that looks like a snowstorm or an old school TV station not coming in properly? Some of you will know that this is background radio frequency noise. It's important to remember that a GPR receiver does not only record GPR signals, it records radio signals. So it records the GPR signals and any other radio frequencies in its bandwidth. To us, these other radio frequencies are unwanted